In order to form an image, we need to look at certain rays. Certain rays that help us to construct the image. And we are going to discuss about 3 or 4 rays that help us to construct the image formed by a concave mirror. Then after, we shall come to the image formed by a convex mirror. Now, the first of the rays which we will consider is called the parallel ray. And here it is. I'm talking from page 24. I'm talking about ray, the first ray which can help us to form an image. And this ray is called the parallel ray. So suppose this is the concave mirror. I'm drawing it on my paper. And this is the pole. And this is the center of curvature. Then this is the principal axis. Okay, so here is the principal axis. Now, any ray, as we learned from concave mirrors, when rays that are parallel to the principal axis and close, rays that are parallel to the principal axis and close to it, like this ray, after reflection, it will pass through the focus. So we call that one the parallel ray. We will need it in constructing the image. So any ray that is parallel to the principal axis will be reflected towards the focus. So that is ray 1. So that is the parallel ray. This ray, after reflection, will head towards the focus. And that is what I've drawn on my sheet. We call it the parallel ray. We will need it in constructing the image formed by a concave mirror. The other ray is called the focal ray. Focal ray. Focal ray. And it is any ray that passes through the focus. Somebody's mic is on, please. Okay. Now, so we have the parallel ray, which after reflection, as we learned the other time, will be reflected towards the focus. And using the principle of reversibility of light, it means if a ray passes through the focus, as I've shown, then after reflection, it will be parallel, as I've done. So we have the parallel ray, which is originally parallel to the principal axis, and after reflection, passes through the focus. And because light can be reversed, it means if a ray originally passes through the focus, as I've done here, then after reflection, it will be parallel. We call this ray the focal ray. So any ray that originally passes through the focus will be reflected parallel. Just as when a ray is already parallel to the principal axis, then after reflection, it will pass through the focus. This one is called the parallel ray, and the ray that passes through the focus is called the focal ray. What is important is what happens after reflection. A parallel ray is reflected through the focus, But a focal ray, by the principle of reversibility of light, after reflection, will be parallel. The next ray that we will need in constructing the image is called the polar ray. The polar ray. That is a ray that incident at the pole of the concave mirror or a mirror. So I'm showing that one too here. So here is the pole, and here is C, and this is the principal axis. Okay, this is the principal axis, and this is the pole. That is the pole. Now remember, the principal axis meets the surface of the mirror at right angle. So it's like a normal, as we said, when the ray passes through the center of curvature, it will be reflected back. So the principal axis is like a normal because it meets the surface of the mirror at 90 degrees. Now, any ray that hits the pole like this will obey the laws of reflection and be reflected that way, so that the angle of incidence here equals the angle of reflection. This ray which hits the pole is called the polar ray. We will need it in constructing our images. The last of the ray is called the central ray. It is a ray that passes through the center of curvature. Central ray. So I'm drawing another diagram here. This is the pole. This is the center of curvature. And this is the principal axis. Now, as we learned already, any ray that passes through the center of curvature, as I've shown here, will meet the mirror at right angles and be reflected back. So the ray is a normal. Apart from this, any ray that passes through the center of curvature, like this one, passing through the center of curvature, will also be reflected back towards the center of curvature, because every radius will meet the surface of the mirror at right angles. So this is called the central ray. The ray that passes through the center of curvature is the central ray. It will be reflected back along the same path, just as in the case of the principal axis. So in order to construct the image for an object in a curved mirror, we will need these four rays. Ray 1, the parallel ray, which after reflection passes through the focus. And then we have the focal ray. This is the reverse of this. When it passes through the focus, after reflection, it will be parallel. Then we have the polar ray, which when it hits the pole of the mirror, is reflected in this manner, so that the angle of incidence is equal to the angle of reflection. In this case, the principal axis is the normal to the mirror. That is, it meets the surface of the mirror at 90 degrees. So it's a normal. And any ray that hits the pole is reflected, so that the angle of incidence here is exactly equal to the angle of reflection there. And the last one is the central ray. Now, any ray that passes through the principal, the center of curvature, will be reflected back along the same path. And this is called the central ray. Apart from the one passing through the principal axis, any other ray that passes through the center of curvature, like this one, is reflected. If another ray passes through the center of curvature, as I've shown here, then after meeting the mirror, it will be reflected back, because it will meet the surface of the mirror at right angle. So it becomes a normal. So all rays that pass through the center of curvature are normals. because every radius of a curve meets the surface of the curve at 90 degrees. If it's a ray, it will be reflected back. So every radius here is a normal. And so the point I'm making is that any ray that passes through the center of curvature is reflected back to the same point and to the center of curvature. Are you with me? Hello?
Yes, sir. Yes, sir.
Yeah.
Okay. I hope you understand the four rays. I've mentioned
Yes,
four
sir.
of them. The parallel ray, ray one, the parallel ray, which is parallel to the principal axis, and after reflection passes through the focus. This is called the parallel ray. Then, because light can be reversed, if any ray originally passes through the focus, as I've shown here, then after reflection, it will be parallel to the principal axis. Then, next we have the polar ray, which hits the pole and is reflected as shown in the diagram, so that the angle of incidence here equals the angle of reflection, and the principal axis is a normal. The last one is the central ray, any ray that passes through the center of curvature. Passing through the center of curvature originally hits the mirror at right angles and therefore is reflected back. So I've shown three central rays, this one, that one, and that one, each of them originally passing through the center of curvature. These are the four rays we need to be able to construct an image when an object is placed in front of a concave mirror. After we finish with concave mirror, I'll come to a convex mirror. Okay, so now go to page 26. Now, from the discussion we have had right now, we are going to look at a ray which is far away, an object which is far away in front of a concave mirror. As we learned the other time, when you show a concave mirror to the sun, which is far away, the rays after reflection will converge at the focus and form an image of the sun at the focus. So when the object is at infinity, the image will be formed at the focus. I'm going to draw that one in a diagram. So here is an object at infinity, like the sun. So here is the concave mirror, the principal axis. This is C, this is F. And the sun is far away, so the rays that reach the mirror will be traveling parallel from the sun. And this ray will be reflected towards the focus, and this one reflected towards the focus to form an image of the sun at the focus of the mirror. So we know that when an object is at infinity, the image will be at the focus. All right? Hello?
Yes, sir. Yes, sir.
Are you with me?
Yes, sir.
So keep in mind, when an object like the sun, which is at infinity, has its rays incident on the curved mirror, concave mirror for that matter. The rays are reflected towards the focus, and when they meet there, they form an image of the sun at the focus. So when U is infinity, when U, the object distance, is at infinity, the image distance equals the focus. All right. Now, what we are going to do next is to bring the object from infinity a bit closer to the concave mirror and see how the image will be formed. So I'm drawing another object. I'm drawing another mirror here, a concave mirror. This is F. This is C. I'm moving the object from infinity to a position behind C. So object behind the center of curvature. When the object is brought near the center, first the object is at infinity. The image is formed at the focus for a concave mirror. Now we are bringing the object closer to the mirror and placing it behind the center of curvature. We are going to use those rays that we discussed to construct the image. So first, there will be a ray from the head of the object parallel to the principal axis, as I've shown. And we know that this is a parallel ray. After reflection, it will pass through the focus. So it will go this way. Then we also know that a ray that passes through the focus will be reflected parallel. So another ray from the head of the object passes through the focus. And after reflection, it will be parallel. Now, these two reflected rays, this one and this one, meet here. So the head of the object will be formed here. At this point, the head of the object will be formed there. And to get the legs of the object, we have another ray from the leg passing through C. And as it passes through C, the center of curvature, it will be reflected back along the same path. So when the head of the image is here, the leg will be formed there, and we have an inverted image. So actually, we don't need all the rays, the 4 rays, to be able to construct the image. Sometimes we only need the parallel ray and the focal ray to be able to know where the image will be formed. So here, the object is behind C, the center of curvature, as I've shown here. A ray from the head, parallel to the principal axis, is reflected towards the focus like this. Then another ray from the head passing through the focus, which is a focal ray, after reflection is now parallel. Now these two reflected rays meet here. So, and since they are coming from the head of the object, the head of the image will be formed there. Now to form the legs of the image, a ray from the legs of the object passes through the principal axis, through the center of curvature, C. And as we know, this ray will be reflected along the same path. And because the head of the image is formed at this point, the legs will be formed there, and we have an inverted image formed like that. So if this is the object, this will be the image formed between C and F. So we have now seen how an object behind the center of curvature forms an image between C and F. Between C and F. Here is the image. Next, I'm going to bring the object closer to the center and place it on the center of curvature and see how we can construct the image. So I'm drawing another diagram here. Object at C. The object is placed at the center of curvature, and I'm drawing another diagram. Here is the pole. Here is the pole. And here is F, the focus, and behind it is C, the center of curvature. Now I'm going to place the object at C here. Here is an object at C. How do we get the image? A ray from the head will travel parallel to the mirror, and as we said, this ray will be reflected towards the center of curvature. So it will go this way. Another ray from the head of the object will go towards the center of the focus, like this, and be reflected parallel. To the principal axis. Now the two reflected rays are meeting here. So the head of the image will be formed at this point because the rays are coming from the head. So after reflection, the reflected rays meet here to form the head of the image. How do we form the legs of the image? A ray from the legs, from the center of curvature, passes through the principal axis, and after reflection, it will go backwards. And because the head is here, the legs will also be formed there at this point, and you have the image formed at the same location as the center of curvature. So in this case, when the object is at the center of curvature, the image is also formed, turned upside down, inverted at the center of curvature. Okay. So object at C, comma, image at C. So that is where the mirror is behaving symmetrically. You place the object at the center of curvature, and the image is also formed at the center of curvature. Okay. Now, next, I'm going to bring the object between C and F. I'm bringing the object closer to the mirror. Remember, at first, the object was at infinity, the sun, and the image was formed at F. Now, I bring the object just behind C, and the image moves from F between C and F here. Now, I bring the object at C, and the image moves back and it's at C. So it's like as the image is getting backwards. So next, I'm going to place the object between C and F and use these rays to construct the image. That is what I'm going to do now. So here, object between C and F. Object between C and F. So I'm drawing the mirror again. Here is the mirror, concave mirror. This is the principal axis. This is F. This is C. This is C. Now I'm placing the object between C and F here. object between C and F. I'm going to use still those two rays. I mentioned 4 rays: the parallel rays, the central ray, the polar ray, and so on. But in actual sense, we don't need all of them to be able to construct the image. So now the object is now at between C and F. We want to look at how the image will be formed. So as we said, a ray from the head of the object traveling parallel to the principal axis, as we said, will be reflected towards the focus. So it goes that way. That is the reflected ray towards the focus. Then another ray from the head passing through the focus like this. This time, as we said, it will be reflected parallel to the principal axis. So it will go that way. It will go this way. And these two reflected rays are meeting here. They are coming from the head of the object. So the head of the image will be formed at this location. That's the head. To form the legs of the object, a ray from the legs passing through the principal axis, as we said, will be reflected back. So this reflected ray will be going back because it's a normal. Then because the head is formed there, the legs also be formed there, and we have the image turned upside down like that. So that is how the image is formed. We have used 2 of those rays we discussed, the parallel ray and the focal ray. These are the ones that we need actually to be able to construct the image. The parallel ray will start from the head, move parallel to the principal axis, and be reflected towards the focus. And another ray from the head passing through the focus, the focal ray, is reflected parallel. These 2 reflected rays meet at this, they actually meet here to form the head of the image. Now, to form the legs of the image, a ray from the legs pass through the principal axis, which is a normal, so it will be reflected backwards. So this ray will be going back. And because the head is here, the legs will be formed there, and we have the image formed there. And you can see that in each, so that's the image form turned upside down. All the images that we have seen so far, each of them is turned upside down from infinity up to where we have gotten now. The next one we want to do is to place the object at the focus. But remember that when the object is at infinity, the sun, the image is formed at the focus. So it means when you place the object at the focus, then the image will be formed at infinity. That is the conclusion. So let's see how that one too will be. Object at F. Object at the focus. So I'm constructing the ray diagram. It's a concave mirror still. Here is F, and here is C. That is the mirror. I'm placing the object now at F. Here is the object at F. And we know already that the image will be formed at infinity, because when the object was at infinity, like the sun, the image was formed at the focus. So now you place the object at the focus, we expect the image to be at infinity. So let's see how we can construct this one. Still using the same 2 rays. A ray parallel to the principal axis, hit the mirror, and it will be reflected towards the focus, through the focus, like this. Okay. Now, in this case, because the object is close to the mirror now, we can have a polar ray, a ray which is going to hit the pole, a polar ray. So we are going to have a ray which will hit the pole like this. We are going to have a polar ray, a ray which from the head of the object hits the pole and is also reflected in this direction. So that the angle of incidence here, because the angle of reflection there, the two are equal. And this is the reflected ray hitting the pole. Now, if you draw this properly, you notice that these two reflected rays, one which passes after reflection passes through the focus, and the polar ray, if you draw it properly, you notice that these two reflected rays are parallel rays. You draw it properly, they will be parallel. And as you know, parallel lines meet at infinity. So these images are these rays are going to meet at infinity to form the head of the image at infinity. Now, to get the legs of the image, a ray from the legs here travel along the principal axis and is reflected back. And because the head will be formed at infinity, the legs will also be formed at infinity. So the image will be formed at infinity. What is the conclusion? Object at F, comma, image at infinity. So going back, when the object is between C and F, the image is formed behind image behind C. So as you bring the object from infinity towards the mirror, the image begins to go back. So to repeat what I just did, I said first, when the object is at infinity, like you have with the sun, the image will be formed at the focus here. Parallel rays will meet at the focus to form the image there. Now you bring the object behind C, and using these three rays, the paraxial ray, the focal ray, and the central ray, the image is formed between C and F. So image between C and F. Image is formed between C and F. Then we bring the object to C. We place the object at C, and using those same rays, the three rays, the paraxial ray, which hit the mirror and is reflected towards the ray, which passes through the focus and is reflected parallel, meeting here to form the head of the image. Then a ray from the legs passing through the principal axis is a normal, so it will be reflected backwards, and the image is at C. Next, we are going to bring the image, the object between C and F, between C and F. So here is the object now between C and F. We are still using those three rays. The paraxial ray parallel reflected through the focus. Then we have the focal ray, which will pass through the focus and be reflected parallel. These reflected rays meet here at this point to form the head. And to get the legs, a ray from the legs passes through the principal axis and it's reflected back because it's a normal and the legs are formed there. So you have the image formed turned upside down. The image is formed behind the center of curvature, C. So you notice as the object is getting closer to the mirror from infinity, the image is going backwards. Next, we place the object at F, at the focus. And from what we learned already, when the object was at infinity, the image is at F. So now if you bring the object at F, we expect the image to be at infinity. So how do you do the construction? The object is at F, and we have a parallel ray from the head. It's reflected through F. But now we cannot have a ray that passes through the focus because the object is now at the focus. So we can now have a polar ray. So another ray from the head through the pole, hitting the pole, is reflected backwards so that the angle of incidence here is equal to the angle of reflection. Now, when you do the construction properly, these two reflected rays will be parallel. And you know, parallel lines meet at infinity. So the head of the image, because these rays are coming from the head of the image will be formed at infinity. Now, to get the legs, a ray from the legs of the object through the principal axis is reflected backwards. And because the head is at infinity, the legs also be formed at infinity, and the image is generally formed at infinity. Now, in all that we have discussed, starting from the object at infinity to object behind C, to object at C, to object between C and F, and object at F. In all these cases, all these 1, 2, 3, 4, 5 cases, the image is always formed turned upside down, inverted, and sometimes magnified, bigger than the image, bigger than the object. It is only at C that the image at C, that the object is the same size as the image. So to recount what we just learned, when the object is at C, the image will be formed very small, diminished at the focus. When the object is brought near behind the center of curvature, the image will be formed between F and C, but diminished, still smaller than the object. Now, when you bring the object at C, then the image will be formed same size as the image. The image will be formed same size as the object. So the image, the magnification here is 1. Then when you bring the object between C and F, now the image is magnified, bigger than the object. And when you bring the object at F, then you form a very large image, many times magnified at infinity. So this is how a concave mirror forms. In all these cases, the image is inverted. In all these 5 cases, image is inverted. It's turned upside down.
Sir, please, I have a question.
Let me finish. The image is, in all these 5 cases, the image is inverted. The image is real. It's inverted and real because the reflected rays actually meet to form the image. So the image is turned upside down and is real in all these 5 cases, but with different levels of magnification. When the image is at the focus, it is the smallest. Between C and F, the image is smaller than the object. When the object is at C, the image is of the same size as the object. Now, when the object is between C and F, the image is behind C, bigger than the object, magnified. And when the object is now at F, the image is most magnified at infinity. But in all cases, what they share in common is that the image is inverted, is turned upside down, and it is real. Now, your question. Your question now.
Sir, please, it's okay. The answer has come. It's okay. Thank you.
Okay. So in the 5 cases, starting from infinity, object at infinity, up to object getting closer to the mirror until it gets to F, in all these 5 cases, the image is turned upside down, inverted, and it is a real image, but with different levels of magnification, depending on the object. The last one we are going to look at is when the object is placed between F and P, between the focus and the pole. We are still pushing the object still closer to the mirror, concave mirror. So the last one will be when the object is placed between P and F, and that is what I'm going to construct now. So object between F and P, the focus and the pole. That is what we are going to construct now. Okay, so let's see. I have the concave mirror this way. I'm drawing it again. Here is the principal axis. Here is F, and here is C, and this is the pole here. Now I'm placing the object between F and P. Okay, how do we get the image? Okay, we are still looking at the rays. First, a ray parallel to the from the head, parallel to the principal axis, as I've drawn. And this ray will be reflected towards the focus. So it goes back through the focus, as I've shown. Then, because the object is now between F and P, we can't have a focal ray. We can only have a polar ray. So another ray hits the pole, as I've shown, and it will be reflected so that the angle of incidence is equal to the angle of reflection. These two angles are equal. So these are the reflected rays, all coming from the head of the object. Now, if you do the construction properly, you will see that these two rays are now diverging. They are spreading out. Remember, when the object was at the focus, the reflected rays were parallel, so they met at infinity to form the image at infinity. Now, the object is between F and P, and these reflected rays are no more parallel, they are diverging. Diverging means they can never meet anywhere in front of the mirror. However, when we produce these reflected rays behind the mirror, like this, like we did for a plane mirror, when we produce these rays behind the mirror, they appear to be meeting at this point. They appear to be coming from this point, which I've shown. So the head of the image will appear to be here. To form the legs of the image, a ray from the leg of the object passing through the principal axis will be reflected backwards. So it can never reach behind the mirror. But if we produce that ray behind the mirror like this, then the leg of the image will be formed at this location, so that here is the image formed. This is the image. Now, this image only appears to be here. The reflected rays are behind them, in front of the mirror. It is only when we produce them behind the mirror that they appear to be meeting at this point. So the head will appear to be here, and the legs of the image will appear to be at this position, so that this is now the image. This type of image is a virtual, this form a virtual image. But you notice that the image is magnified, is bigger than the object. So when the object is between F and P, the image is now on the opposite side of the mirror, virtual and magnified. Virtual, magnified, and upright. So the image is virtual, magnified, and upright. This is very different from the 5 cases that we've discussed. In the 5 cases that we discussed, the image is always real and is inverted, but with different levels of magnification depending on where the object is placed. But in this particular case, when the object is now between F and P, the image is virtual. It's not real. It's virtual. The image is virtual. It is magnified, bigger than the object, and it is upright. In all the 5 cases, the image was inverted. In this only case, the image is upright, magnified, and virtual. Virtual means that it only appears to be there. It is actually not behind the concave mirror. It only appears to be there, virtual. So you take note of this particular one, which deviates from the other 5 cases. Now, because a concave mirror with the object between F and P form a magnified, upright, virtual image, we can use the concave mirror as a magnifying mirror, so that when you go to the hospital with a dental problem, the dentist wants to examine your teeth. He will use a concave mirror, place your teeth between F and P in order to see a magnified image of your teeth, upright, like your teeth is standing, and he can now examine it properly. So concave mirrors can form both real images and can also form a virtual image when the object is between F and P. And the application of the concave mirror in this sense is that it is used by dentists to examine teeth of patients. How do they do it? They will bring the mirror so close to the teeth that the teeth will be between the focus and the pole. And in this case, the dentist will see a magnified image of your teeth standing upright the way it is, so that he can examine it well. I want you to take note of this particular case when the concave mirror is forming a virtual image. Remember, in all the 5 cases, from the object at infinity, object behind C, object at C, object between C and F, and object at F, all these 5 cases, the image is real, it is inverted with different levels of magnification. The smallest image is when the object is at infinity and the image is at F. The biggest image is when the object is at F and the image at infinity. In all these cases, the image is turned upside down and it is real. In this particular case, when the object is between F and P, the image is virtual and is upright, erect, and is magnified. Because of this property, Dentists use concave mirror to examine teeth by placing the teeth between F and P and examining the magnified image. I hope it's clear.
Yes, sir.
Yes, sir. Sir.
So you have to learn how to construct these images. Object at infinity, the image is at F. Object is behind C. The image moves back between C and F. The object is at C. The image is at C. So the only case where in a concave mirror, the image and the object are at the same location is when you place the object at the center of curvature. In this case, the size of the image is the same as the size of the object. The image is inverted, turned upside down, and it is real. But keep in mind, all the 5 cases before, the image is real and inverted with different degrees of magnification. In this particular case, when the object is between F and P, the image is not real, it is virtual. And it's upright, erect, but magnified. I hope the point is made. Those diagrams you see there, you look through, you see all of them. Look at the first one is when the object is behind C. The next one is when the object is at C, the diagrams.
Sir.
Yes. Yeah.
Please, with the object between the F and the mirror, because of the rays did not cross each other. That's why it diverged.
Yeah, when you draw it properly, the reflected rays will spread out. They will diverge.
Okay.
When you construct it properly, the reflected rays, these reflected rays will diverge. And once they diverge, it means they cannot meet anywhere in front of the mirror. So when we produce them behind the mirror, they appear to be coming from here. And the head of the image is forming there. To get the legs, a ray from the legs hit the mirror, it will be reflected back. It will not come behind the mirror. So when we produce the ray behind the mirror, then the leg will be formed there, the image is formed there. So this is the only case where a concave mirror forms a virtual image. So take note, a concave mirror can form both real images and virtual image in only one case, when the object is between F and P. So you refer to the diagrams and you'll be convinced of what I just mentioned. Okay. Now, so the last diagram on page 28 is when the object is between, the object O is between F and P, and the image is formed behind on the other opposite side of the mirror, and it's upright and it's magnified and it's virtual. So take note of this. They can come in your objective test. Now, what I'm going to do next is image formed by convex mirror. How a convex mirror also forms an image of an object when it is placed in front of it. I hope it is clear.
Yes, please. Yes,
sir.
Good. I'm going to image formed by convex mirror, page 29. Right. So, image formed by a convex mirror. I'm just going to draw it. So let's say we have a convex mirror. Here is a convex mirror. This is the principal axis. This is the reflecting surface. And we place an object anywhere in front of the mirror, like this. We are going to use those rays. Now, first, so here will be this is the F, and this is the C. Inside, not this time outside here, the F and C are on this side of the mirror, because it's curving this way. It's a sphere. So the C will be here, center will be here, and F will be there. And then come on. Fabat or battery bra, or charge and brad count low battery. Oh, you Type C. Or it's ordinary one. Count by what connect my own slow battery. But okay.
That's what.
Okay. All right. Back to you. Now, we are now looking at a convex mirror. Convex mirror. Convex mirror. How we can extract the image. Now, because it's a sphere, the center of curvature will be somewhere here, the focus will be there, and the inside is silver, the outside is polished. So we can place the object in front of it. Okay, so we are using the rays. First, a ray from the head of the object will travel parallel to the mirror, and because it is parallel, it will be reflected as if it is coming from the focus, like this. Reflected this way, as if it is coming from the focus. It will be reflected this way, as if it is coming from the focus. Next, we are going to have a polar ray. A ray that will hit the pole here from the head. So we construct a ray from the head, it hits the pole, and it's going to be reflected this way so that the angle of incidence is equal to the angle of reflection. This ray is reflected backwards. Now, when it reflected in front of the mirror, when we produce it behind the mirror, so the head of the image will be formed at this point. To get the legs of the image, a ray from the legs, also through the principal axis, will be reflected backwards. When we produce it behind the mirror, it goes that way. And because the head of the image is formed here, the leg of the image will form there, and we have a virtual image because we only produced the reflected rays behind on the other side of the mirror. I'm going to repeat. Here is the object in front of the mirror. We are going to construct the image. A ray from the head traveling parallel to the principal axis is reflected as if it is coming from the pole. So when you produce a reflected ray behind the mirror, then as if it is coming from the center of curvature, like this. Sorry, coming from the focus. Now, another ray from the head of the object hit the pole and is reflected in this direction so that the angle of incidence equals the angle of reflection. Now, when you produce this reflected ray also backwards, these two rays that are produced appear to be meeting here. So the head of the image is formed at this location. Now, to form the leg of the image, a ray from the leg of the object through the principal axis is reflected backwards. So it will never get behind the mirror. When we produce it behind the mirror, the leg will be formed here, and we have a virtual image formed on the other side of the mirror between the pole and F. And this is always so. No matter where you place the object in front of a convex mirror, the image is always formed between the pole and F and is virtual. So image is always between P and F. Here, between P and F, the image is virtual because the rays don't reach there. We only produce them. And it is upright. The image is erect and is diminished, the image is always smaller than the image, the object. The image is always diminished. So these are the characteristics. The image is always formed between P and F, the pole and the focus. The image is always virtual because the rays actually didn't reach there. We only produce them behind the mirror to reach this position. So the image is virtual. The image is always smaller than the object. It is diminished. And the image is always upright. So a convex mirror always forms virtual, diminished, and upright image always between the pole and F. No matter where you place the object, you still get the same virtual image, upright image, diminished image between P and F. This is for a convex mirror, no matter where you place the object. No matter where you place the object, you still have the same characteristics of the image. Unlike a concave mirror, in which in some 5 cases, the image is real, and in only 1 case, the image is virtual. So a convex mirror always forms virtual image. The image is diminished, the image is upright, the image is virtual, and the image is always between P and F. This is seen in diagram 29. Are you with me?
Yes, sir.
Yes.
Yes, sir. Yes, sir.
Hello.
Yes, sir.
So near the diagram, write image and underline it and write virtual. Near the diagram, page 29, A and B, write image, virtual, diminished, upright, between F and P. That is always the case for a convex mirror. Are you done?
Yes, sir.
Are you done?
Yes, sir.
And keep it in mind. A convex mirror always forms a virtual, diminished, upright image always between P and F. All right. A convex mirror does this. It is used practically in car driving mirrors. All the driving mirrors of vehicles are convex mirrors so that they form the image for the driver to see. And another reason for using convex mirrors is that they have a wide surface, wide reflecting surface, so it can cover a wide area behind the driver. So for 2 reasons, convex mirrors are used as driving mirrors for vehicles. 1, they always form an image, and it has a wide surface, so it can allow the driver to see a wide area behind him. So convex mirrors are used in driving mirrors. I told you concave mirrors are used by dentists to examine teeth. But both mirrors can be used in telescopes. We call them reflecting telescopes. So they both can be used in a single telescope called reflecting telescope. But a concave mirror alone can be used as it can be used by a dentist to examine teeth, and a convex mirror is used in car driving mirrors. All right. Now I'm moving on.
Please, can I ask a
By
question?
using this ray diagram, we are able to, okay, ask.
Please, in the production of all these images,
Ask your question.
yes, please, I'm asking. In the production of all these images, either by a convex mirror or a concave mirror, the distance correct, and then the center of curvature. Is
Oh, your
there is
line is
there any rule
breaking.
that they should always
Ask
be
your
the
question. I
same,
didn't
or
get you. Your line is breaking. I'm not getting your question.
okay? So I'm asking that in the production of
Hello.
all these images. So please, let's continue.
I'm not getting your question. Your line is breaking.
Okay, let's continue.
Hello. Hello.
Please repeat
Yeah,
what you said.
Hello.
Sir, please, he said we should continue.
Your line is breaking. Yes.
Please, can you hear
Sir,
me
he
now?
said,
Let one person ask your question so that I can get it.
Please, I'm asking that in the production of all these images, either by a convex mirror or a concave mirror, is there any criteria for the distances between the pole and then the focal point and then the center of curvature? Is there any criteria that the distances should be the same before you can get the images correctly, or you can just take any distance?
First, we discuss when the object is at infinity for concave mirror, very far away, the sun. And we notice that the image will form at the
I
focus.
understand.
Now we are coming to the.
I'm asking for the measurements. When you are drawing yourself.
Now we are coming to where measurement is involved. We have something called the mirror formula, right? The mirror formula,
Okay, sure.
where we are
All
going
right,
to
let's
use
continue.
measurements. We are going to use measurement. So our next topic is the mirror formula. Here we are going to use measurements, not approximations, as we have said, between this and this, behind this, and no. We are going to look at crop in cases where there are actual measurements. So our next subtopic is the mirror formula, right? So
okay, thank you.
We are looking at the mirror formula. The mirror formula. The mirror formula. Now, we can use the ray diagrams to obtain the image and describe it. Either it's erect, it's virtual, it's between P and F, it's between wherever behind C. We can use ray diagrams to get the image and describe it. We can also use a certain formula to arrive at the same conclusion, and we call that one the mirror formula. So I'm going to help you to know what the mirror formula is about. Go to page 33. There are different types of them in your book. We are going to look at only one of them, page 33. Go to page 33. We are looking at the mirror formula there. Now, with the mirror formula, we are going to do measurements, measure object distance, image distance, and all that. The mirror formula. Now, first, notice that anytime a mirror forms an image, the height of the image, divided by height of the object is called magnification, M. Note that. And if the image is at a certain distance, which we normally call V from the mirror, and the object is at a certain distance, which we call U from the mirror, then V over U is also equal to the magnification. Anything about the image divided by anything about the object is called magnification. So size of image divided by size of object height of image divided by height of object, image distance divided by image distance, all give the same result called magnification. Now you notice that in the concave mirror, when you place the object at C, the image will be formed also at C, same size.
Please, sir, we don't see your board.
Object. So there'll be... Say it again.
Yeah, we can't see your board well.
Okay. Now, is it? Can you see now? Can you see it now?
Yeah, sir. Now it's okay.
So I'm talking of magnification. You are trying to find out the number of times the image is bigger than the object. And it's size of image divided by size of object, height of image divided by height of object h naught, image distance, which we usually call V, divided by object distance, which we denote by U. All these ratios give a certain number we call magnification. When the magnification is 1, it means the image size is the same as the object size. There's no magnification. So that is the first thing we need to know. This type of magnification, in which we are comparing the height of the image to the height of the object, is called lateral magnification. Lateral magnification. Keep in mind, lateral magnification. Height of image divided by height of object, image distance divided by object distance, or anything about the image divided by that of the object gives us the magnification. It's a way of comparing the number of times the image is bigger or smaller than the object. If you get a number greater than 1 for magnification, it means the image is magnified. If you get a number equal to 1, there is no magnification. If you get a number less than 1, the image is diminished. It's a fraction. The magnification will be a fraction, and it means the image is diminished. So that is about magnification. Now, so that is 1. 2, I'm going to have a concave mirror. I'll place an object in front of it and then form the image using the ray. So here is what you see on page 33. On page 33. So here is the concave mirror, principal axis. Here is C. Okay, I'll indicate F here. And I'm going to place an object behind C for simplicity. An object of height h naught behind C, and then construct the image. Now, I'm going to use a polar ray and a central ray for this purpose. So I'll have a ray going towards the pole, like this. It will be reflected in this direction, so that the angle of incidence here is called the angle of reflection. Then I'm going to have another ray pass through C. And as we said, any ray that passes through C is a normal. So you have a ray going through C, and it's reflected backwards through C. Since these two reflected rays are meeting here, the head of the image will be formed there. The head of the image is formed at this position because these two reflected rays are meeting here. Head of image formed there. Now, how do we get the legs of the image? Another ray from the head of from the leg of the object go through C this way, and it's reflected backwards. Since the head is formed here, The leg we form there, and we have an image turned upside down like that. An inverted real image, an image turned upside down but real. Remember that this angle here is the same as that angle. Apart from this, some two other angles have been formed in some triangle. Look at this triangle. So let me call this one height of object here. The height of the object here, height of object, this one, height of object. And this is height of image. Two other angles have been formed here. This angle here and this angle there. And you see that they are equal. Can you see that they are equal? They are opposite angles. So they are equal. Okay? Let me call these two angles that are equal alpha. Angle alpha. They are equal. The angle formed here and this one are opposite. So they are equal. Let's call that angle alpha. Now, we are going to use trigonometry. Tan alpha for this one, for this triangle here, is a right angle triangle. So tan of the angle alpha is going to be the height of the object h naught. But let me also indicate here. Now you mentioned distances. So if the object is here, pay attention, then this distance is u, the object distance here. All right. Now, this is the image. From the mirror to the image here, this distance is v. The image distance from the mirror to the image is image distance v. From the mirror to the object is object distance u. The last distance is c, here, c. From c to the mirror is the radius of curvature. We told you that the distance from the pole to center of curvature is the radius of curvature, r. All right? So, with this, we want to find the tan of the angle alpha in this diagram. It is going to be opposite h naught divided by the adjacent, this distance here, between here and there, here. This distance is u minus r here. From here to here is u, from here to here is r. So this distance is u minus r. So tan alpha is u minus r for this triangle. For the second triangle involving the image, this triangle, tan alpha will be the height of image opposite over adjacent here. So tan alpha, the same tan alpha, is opposite. The opposite is the height of the image divided by this distance. The distance I'm showing here. This distance is c minus v. The image distance here is from here to here, c, minus from here to here, v. But this distance from c to v is r, the radius of curvature, r. So this short distance is from here to here, r, minus from here to here, v. So r minus v. Okay, so from the first triangle involving the object, tan alpha is h naught, height of object, divided by this distance, which is u minus r. I've written it here. Then for the second triangle also involving the angle alpha here, tan alpha equals opposite, which is height of the image, divided by this short distance. This distance is from here, c, to P minus this one, which is V. So it is R minus V. I've written it down here. So I have tan alpha equals H naught over U minus R. And I also have for the first triangle, and I also have the second triangle involving the image, tan alpha equals height of image divided by R minus V. So I'm going to repeat everything here. So I have in one case, first, I notice that I over H naught equals V over U for magnification. Then I also have an alpha equals H naught over U minus R. And then I also have tan alpha equals H naught over R minus V. R minus V. All right. Now, so because this is tan alpha, this is tan alpha, it means they are equal. These two are equal. So I'm going to equate them. This is tan alpha, H naught over U minus R. I also have tan alpha for the second triangle, HI, height of image, divided by R minus V. Okay, so here is height of image divided by R minus V, and this is height of object divided by U minus R from the ray diagram. But this tan alpha is the same as tan alpha here. So it means these two are equal. So I'm going to write H naught over U minus R equals height of image over R minus V. What I'm going to do next is mathematics. It's not physics. I'm going to send this one, the denominator here, up and bring the height of object down. I'm bringing this one up and bringing this one down. When I do so, I'm going to get R minus V over U minus R equals HI over H naught. But HI, height of image over height of object, is the same as V over U. So I'm going to have this equals V over U. So finally, I have R minus V over U minus R equals V over U. What I'm doing is mass. Now I'm simplifying, I'm going to cross multiply. I'm cross multiplying to make it linear. So you are going to have U multiplying R minus V and V multiplying U minus R. So something like this. So you have U times R minus V equals V times U minus R, like that. Okay, now I'm going to expand. What I'm doing is mass. When I expand, I'm going to have UR minus UV. So UR minus UV equals, when I expand this one, I'm getting another UV here, UV minus VR. Okay, so on the left-hand side is UR minus UV. On the right-hand side is UV minus UR. So I'm going to group like terms. I'll bring this UV to this side and bring this one the other side. So I'm going to get UR. I'm bringing minus VR to this side. So it will be plus VR equals UV here plus another UV, making 2 UV. So Right. So I have, after I expand and group like terms, listen to me carefully. This is UV minus UV, and here is plus UV. So I'll move this minus UV to this side, so that I have 2 UV, and move this minus VR to the other side. That will give me UR plus VR equals UV plus UV. So you are going to get something like this. You are going to get UR plus VR equals 2 UV. That is UV plus UV is 2 UV. Now, I'm going to divide everything here. Divide everything here by UVR. I'm going to divide both the left-hand side and the right-hand side by UVR. UVR. U times V times R. When I do so, I'm going to get UR over UVR plus VR over UVR equals 2UV over UVR. Now I can do some cancellation. This R will cancel this. This U cancels that, leaving 1 over V plus. R cancels R, V cancels V. I have 1 over U equals U cancels U here. V cancels this. I have 2 over R. All right. So this is the equation that I have. 1 over image distance plus 1 over object distance equals 2 over the radius of curvature. Now I want to simplify this one further. We notice in our discussion that when U equals infinity, when U is infinity, infinity means when U is at infinity, V will be at F. When the object is at infinity, the image distance is F. That is what we notice from our ray diagrams. When the object is at infinity, the image will be at the focus. So when U is infinity, V is F. We substitute this one into what we have got, the equation, and we have, when U is infinity, V will be F. So here is going to be 1 over F for the V, 1 over V, plus 1 over infinity equals 2 over R. Now, 1 over infinity is 0. 1 divided by a very large number is 0. So it means we have 1 over F equals 2 over R. We have 1 over F equals 2 over R. Or we have R equals 2F. The radius of curvature equals twice the focal length. So when we bring this into the equation that we wrote here, which is 1 over U plus 1 over V equals 2 over R. When we bring this R, put this equation here, replace the R by the 2F, then we get 1 over U plus 1 over V equals 2 over 2F. And this cancels that, giving us 1 over U plus 1 over V equals 1 over F. And this is what we call the mirror formula. 1 over U plus 1 over V equals 1 over F. This is one of them. Number 2, R equals 2F. So twice the focal length equals the radius of curvature. That is equation number 2. So this is equation number 1. We call this the mirror formula. 1 over object distance plus 1 over image distance equals 1 over f. Then equation number 2, in the derivation, we saw that the radius of curvature equals twice the focal length. These are the equations we use for mirrors, 2 of them. We call this the mirror formula, and this one is help us to determine the relationship between the radius of curvature and the focal length. So we have the mirror formula. Everybody keep in mind, 1 over u plus 1 over v equals 1 over f. Here, u is the object distance, v is the image distance, f is the focal length. In equation 2, r is the radius of curvature, f is the focal length. These are the equations about a curved mirror. We shall also see later that they apply to lenses as well. So that is the mirror formula. Now, when you open to page 35, page 37, they all talk about the same thing. They all deriving the same mirror formula in different ways. But we have discussed this is enough. The mirror formula. Now, in order to use this mirror formula, you have to adopt a certain rule. Adopt a certain rule. We call it convention. Use this formula correctly and get your results, the results that you deserve. You need to adopt a certain rule called the conventions, the mirror convention. And what is this convention or rule? In order to use this formula, the rule is that, here is the rule, I'm writing it down. Here is the rule to use this mirror formula. 1 over u plus 1 over v equals 1 over f. You use this convention or this rule. The rule is that let me get another marker. The rule is that real is positive. Real is positive. Virtual is negative. So when there is a real object, it will be positive. When there is a virtual object, it will be negative. That is, when there is a real image, it's positive. When there is a real object, it is positive. When there is a virtual image, it is negative. When there is a virtual object, it will be giving the sign negative sign. It will be giving a negative sign. Apart from this, a concave mirror. Concave mirror.
Sir, please,
yes.
Please take it again. The mirror convention.
Okay. The mirror convention is that it's real is positive. And by implication, virtual is negative. You know that in discussing this, sometimes the image is real, the image is virtual. A convex mirror always forms a virtual image. A concave mirror, in many cases, 5 different cases, form real image. Only 1 case is form virtual image. To apply this formula to solve any problem, the convention is that real is positive. And by implication, virtual is negative. What does this mean? Any real object or real object distance or real image distance is positive. Any distance or virtual image is negative. So that is the meaning of real is positive. That is the convention. Anything real, that is where the rays actually meet to form an image, will be given a positive sign. Anytime we only have to produce the reflected rays somehow, in order to form the image, we'll form a virtual image and we give that virtual image a negative sign. So real is positive. The other thing that you need to keep in mind is that if you take a concave mirror, it will reflect parallel light and they will meet at the focus. So the focal length, the distance from the pole to the focus, is real. The radius of curvature is also real. They are all positive numbers. For a concave mirror, the focal length, which is the distance from the pole to the focus, is real, is positive. The radius of curvature from the pole to the center of curvature is also real. It is always positive for a concave mirror. For a convex mirror, however, because the rays only appear to be meeting at the focus, the focal length of a convex mirror is negative, and its radius of curvature, which is twice the focal length, is also negative. I hope it's clear.
Yes, sir.
So concave mirror, focal length, distance between focus and pole, positive. Radius of curvature, distance between the pole and the center of curvature, positive. Convex mirror, in this case, the parallel rays hitting it diverge and only appear to be coming from the focus. So the focal length, the distance from the pole to the focus, is negative, and because of that, the radius of curvature, which is twice the focal length, is also given assigned a negative number. But now, lastly, in order to name a mirror, you have to mention its focal length. That is how we name a mirror. So you can say, I'm going to buy a concave mirror of focal length 20, or I'm going to buy a convex mirror of focal length -10. You name a mirror by mentioning the focal length, which is the distance from the pole to the focus. Remember, the distance from the pole to the center of curvature is the radius of curvature. But we name a mirror by mentioning its focal length. That is how we label a mirror. So you buy a mirror, you label it, you put a small sheet of paper, you write F equals +10. It means this is concave mirror, the focal length, which is twice the radius of curvature, is 10. So if you buy a concave mirror and they've written on it F equals 10 +10, it means the focal length is 10 centimeters, whatever the unit. It means the radius of curvature is going to be twice, which is 10 times 2, 20. So the focus divide the radius of curvature exactly into 2. Anytime you are drawing a ray diagram, you have to observe that. Where you put the focus must be exactly between P and C. Exactly in between them, that is where your focus is. You don't put the focus anyhow. If the radius of curvature is 20, the focal length is 10, halfway between P and F. Okay, now that we've seen the mirror formula and the other formula involving the radius of curvature and focal length, and we've seen the convention for using this formula, real is positive, we can now apply the formula in solving simple problems. So let's see. Let's say you have a concave mirror. Here's a concave mirror. And here is your C. Here is midway between P and F. You see, midway between C and P is your F. So this distance is your focal length. And this distance is. So this point is exactly between P and F, halfway between them, twice of F. Now, let's say you are told that in a certain concave mirror, an object is placed. Okay, let's say the focal length, I told you, you name a mirror by mentioning the focal length. So let's say you have a concave mirror of focal length, let's say 10 centimeters, and this number is going to be positive. If it were to be a convex mirror, this number will be negative. So let's say you have a concave mirror labeled f equals 10 centimeters. Now you place an object U at a distance, let's say 30 centimeters from the mirror. You put an object at a distance 30 centimeters. Question: where will the image be formed? What is the image distance? And 2, what is the magnification? Then you apply the mirror formula and solve. You are going to say 1 over f equals 1 over u plus 1 over v. Then you do your substitution. F is 10. For a concave mirror is plus. So 1 over 10. The image distance, you place the object 30 centimeters away from the pole. So the image distance will be 30. So 1 over 30 plus 1 over v. Then you solve for v. How do you solve for v? You know how we deal with fractions, right? When you are adding fractions, you find the LCM. You find the LCM first. So
Yes,
we
sir.
have 1 over v plus 1 over 30 equals 1 over
V.
over 10, right? Huh?
Oh, 1 over 10 is equal to 1 over 30 plus 1 over V.
Correct. So 1 over v plus 1 over 30 equals 1 over 10, right?
Yes, sir.
Okay, now you know they are fractions, and with fractions, if you want to solve them, you have to find the LCM. So on the left-hand side here, 1 over v plus 1 over 30. You have to find the LCM. The LCM is 30v.
V.
So v goes here 30 times. So here will be 30 plus 30 goes here v times. So v equals 1 over 10. Then you can cross multiply and have 10 times 30 plus v, like this. 10 times 30 plus v. When 10 multiplies this, and 30v multiplies 1, so giving you 30v. Then you expand, the rest is mass. 30 times 10 will be 300. 10 times v will be 10v, and this is 30v. Then you group like terms, 10v here, 30v. So you move the 10v to the other side, and you have 300 equals 30v minus 10v. So you are going to get 300 equals 30v minus 10v gives you 20v. Okay?
Yes, sir.
Right. So you divide through by 20. And this cancels that. And 2 goes into 30 15 times. So 15 centimeters is the image distance. The image distance is 15 centimeters. Now, the other question is, what is the magnification? The magnification is height of image. Magnification is
Height of the
height
image
of
of the height of the
image
object.
over, which is the same as v over u, right?
Yes, sir.
V over u. What is v?
V.
30 centimeters.
I said,
Okay, so
U is
sorry.
30 centimeters.
V is 15 centimeters. And u is what? 30.
30.
So the magnification is half. The image is reduced by half in height. All right?
Yes, sir.
I can give you another one with a convex mirror. What would be the if this were to be a convex mirror? If you are told that an object is placed 30 centimeters in front of a convex mirror, if the focal length is 10 centimeters, find the image distance. Then in the substitution, F will go in as negative number. Is that right?
Yes, sir.
Hello?
Sir.
Hello?
Yes, sir.
Yes, sir.
Hello?
Sir, please, we can
Sir.
hear from you.
Uh-huh. Uh-huh. Hello?
Sir, we can hear you.
Okay. If the mirror were to be convex, then in the substitution, the focal length, which is 10, will enter the formula as a negative number. And you do the mathematics, find the LCM, the blah, blah, blah. Whatever you get will be your V. All right. So that is about that. The mirror formula and how it is used using the convention. Okay. Now, apart from this formula, we can modify this formula into others. We can modify the form using mathematics. We can modify this formula and write other formulas that are similar to it. We can modify the mirror formula into other formulas which are also useful using mathematics. What is the mirror formula? 1 over U plus 1 over V equals 1 over F. And M, magnification, equals V over U. These are the two formulas, but we can modify this formula and get other formulas that are also useful and can be used in calculation. For instance, if we multiply through the mirror formula by V, if we should multiply all this through by V, we are going to have
U.
V over U plus V over V equals V over F. Now, V over V will be 1. V over U is magnification M equals V over F. Or magnification equals V over F minus 1. We can use this if we want. This one is also part, it's a certain form of the object distance, focal length, and that is it. If we should multiply the mirror formula, instead of multiplying through by V, we multiply through by U, the object distance. We get another form which is also useful. Okay, but it's enough to have this, that, and that. Have 1 over U plus 1 over V equals 1 over F. Magnification equals V over U. And when you multiply through the mirror formula by V, you get finally magnification equals V over F minus 1. Okay. So
Sir.
for instance, in this particular case, let's say you are told that a certain object is placed in front of a, or as I said, you can multiply through by U and get another form of it. If you do so, you are going to have U over U plus U over V equals U over F. U over U is 1. So you have 1 here plus 1 over magnification. U over V is 1 over magnification equals U over F. And here too, you can make the magnification subject. And when you make the magnification subject, you have a formula involving U and F. So if you are told that in a certain a concave mirror, it produces magnification of say 3, the focal length is, let's say, 30, find the object distance. Then quickly you use this to calculate. Is that right?
Sir.
Yes.
Sir. Please, with a question, just solved. Let's say a question like, say, you should determine the image of the, you determine the nature of the image. How are you determined?
When you calculate the image distance, right, and you get a positive number as your image distance, it means the object, the image is real. Remember, real is positive. But when you calculate, for instance, in the calculation that we did, we got V to be 15 centimeters. The real. All right. So the nature of the image is that, so real is positive, virtual is negative. So even when you get a negative answer for the image, you will conclude that the image is virtual. When you get a positive answer for the image distance, it means the image is real. That's the nature.
Okay. Thank you, sir.
To know the true nature, you have to draw the diagram to know where it is. And remember, in concave mirror, when the image is real, it means it is inverted. It's turned upside down. Right. So you can try your hands on some of these examples of using the mirror formula, and then you know what it is. If it's negative, it's virtual. If it is real, if it is positive, it's real. So real is positive. That's the convention. Okay. So that is about reflection at curved surface. You can go through the other examples and follow what we have done. In particular, when you are adding fractions, you must look for the LCM first before you go ahead. So we are done with curved mirror. Session 4. Can we move to session 4?
Yes, sir.
Okay, we still have some time. It's a what's the time? Okay.
5:21.
5:20.
Okay, let's end at 6, right?
Okay.
Let's end at 6. So I'm going to session 4. We have seen reflection at plane surfaces. We have seen reflection at curved surfaces, concave and convex mirror. Now we are going to look at refraction of light. So that is where we are now, session 4. We have a lot to do, but we can move gradually, and if we add some other periods to it, we'll be able to move forward. Okay, so let's look at refraction of light. Refraction of light. Refraction. Let's see if this one will be clear. Refraction of light. Okay, now in our everyday experience, in our normal, natural, everyday experience, sometimes we observe a rainbow in the sky after rain. Sometimes when you are moving, you are on the hot tar road, cold tar road in the afternoon in a car, and you look ahead, you think there's a pool of water on the road far away. We call this one mirage. When you stand near a pond, a swimming pool, and you look at the bottom, you think it is shallow. Meanwhile, the pond will be very deep, but you think it is shallow. Also, when you place a stick, half in water and half in air, you put water in a cup, and then you put your spoon inside the water. So half of the spoon will be in the air, part of it will be in water. And you look at the spoon at the surface, you think the spoon is broken into two, or broken, bent or broken somehow. All this, and when you pass light through a triangular glass prism, you see the 7 different colors. All these effects are due to a concept we call refraction of light. So refraction is a property of light. Now, what is refraction? Know this. Empty space is called vacuum. Empty space is called vacuum. That is empty space. Any other material that light can pass through is called transparent medium. Transparent medium. Any material that light can pass through, like air, like glass, like water, anything that light can pass through is referred to as a transparent medium. Now, when light travels through empty space, it travels at a speed we denote by C equals 3 times 10 to the power 8 meters per second. That is the speed of light in empty space. 300 million meters in 1 second. That is the speed of light in empty space. Anytime light passes through any other transparent medium, like glass, like water, like air, then it will slow down. It will slow down and also change direction. Anytime light travels into any medium, transparent medium apart from vacuum, it will slow down. It will travel at a speed less than 300 million meters per second, and also change direction. Now, speed and direction is called velocity in physics. So we can say that anytime light travels from vacuum to any transparent medium, it will change its velocity, which means it will change the speed, reduce the speed, and also change direction. So what is refraction? Refraction is the change in velocity of light when it moves from one medium to another. All right? Refraction is the change in speed and direction of light when it moves from one transparent medium like vacuum to another transparent medium like air or water or glass. So change in speed and direction from one medium to another, or change in velocity of light when it moves from one medium to another. This is the technical definition of refraction. It is this change in velocity that caused the mirage, that caused a pond to appear to be shallow, that caused a spoon to appear to bend, that caused the rainbow in the sky. Change in the velocity of light when it moves from one medium to another. Or you can say refraction is the change in speed and direction. Speed. Then it was refraction. So refraction is a property of light. It is the change in velocity of light when it moves from one medium to another. Well, you know, when you go to the sea, you go to the sea, there are fishes there, and the fishes must see and feed. For the fishes to see and feed, light from the sun must travel through the vacuum and come through the atmosphere, enter the sea, and help the fishes under the sea to see. So in all this, light undergoes various refraction. Those who use lenses, spectacles to see, when you use a lens to see, the lens lets the light undergo refraction. The light undergo refraction in the lens, and even in your eyes, there are some lenses and fluids, the vitreous humor and the aqueous humor, which all together refract light in your eye for you to create an image for you to see. So refraction is the change in velocity of light when it moves from one medium to another, or change in speed and direction of light when it moves from one medium to another. So that is the basic definition of refraction. But what is left is I'm going to draw a diagram and label the diagram and mention the laws of refraction, and then we can quantify the loss of refraction into an equation which we can use to do our calculation. So let's say here a piece of glass. I'm drawing a piece of glass here, glass, and then above it is air. Here is air above the glass. If I use a pencil, can you see?
Yes, sir.
Can you
Yes,
see
sir.
the pen? Can you
Yes,
see
sir.
the pen?
Yes,
You
sir.
can see. Okay.
Yes, sir.
So here is a piece of glass, and surrounding it is air. So this is glass, and surrounding the glass is air. Now, here is a normal to the glass, a line that passes perpendicular through the glass is the normal. When light moves from air and hits that point, then part of the light will be reflected by the glass, and part will pass through, will be transmitted through the glass. And the part that goes through the glass is going to undergo refraction. If the glass were not there, the light would have continued in this direction. But because the glass is there and the light is passing through, it will change direction and go in a different direction like that. So here is the normal. This ray is the incident ray. The ray in the air coming towards the boundary between air and this is the boundary between air and glass. Here is the boundary. And the ray hitting the boundary from air is called the incident ray. Of course, I said the ray will be, part of it will be reflected. We are not interested in the reflection, so we will ignore the reflected ray. We are interested in the part that will pass through the glass and then undergo refraction. And so this is the refracted ray. Now, this point where the incident ray hit the boundary is called the point of incidence. And some angles have been formed. This angle formed between the normal and the incident ray is called angle of incidence. The angle formed between the refracted ray and the normal, this angle, how? It's called the angle of refraction. So we have angle I, angle of incidence, and angle R, angle of refraction. Now, there is an angle here between the original path of the ray and the refracted ray. This angle is called the angle of deviation. It has deviated, the angle of deviation, D. So we have three angles formed. Angle of incidence between the normal and the incident ray, angle of refraction, between the normal and the refracted ray, and the angle of deviation between the original path of the ray and then the new path, the refracted ray. This angle is called the angle of deviation. You will notice that the angle of incidence equals the angle of deviation plus R. This angle is opposite the whole of this. So I equals D plus R. I equals the angle of deviation plus the angle of refraction. All right? Okay. And what I've just discussed is called refraction. Now, let's look at a property of transparent media called refractive index. Refractive index is a property of all transparent media called refractive index. We denote it by a prolonged N like this, an N written like this, refractive index. So if I want to write refractive index of glass, I'll write this and write small g here. If I want the refractive index of water, I'll write it and write W there. For air, I'll write it and write small a there. And I mean the refractive index of air. So refractive index of glass, of water, of air, and any other material, I'll write the N and write a small symbol there. Refractive index is a property of all transparent materials. What does it mean? Refractive index, what is the meaning? Okay, this is what it means. We told you earlier that light travels in vacuum at a speed c equals 3 times 10 to power 8 meters per second. That is 300 million meters per second in vacuum. In vacuum. And that anytime the light enters any transparent medium, 1, it will slow down, and 2, change its direction. So let's take this glass and let's take the medium above to be vacuum. So here I'm doing it again. Here is glass, a piece of glass, and surrounding it is vacuum, and light is coming from vacuum into the glass. We know the speed of the light in vacuum, C, equals 3 times 10 to power 8 meters per second, 300 millimeters. Now, when it enters the glass, it will slow down to a new speed, V, a new velocity or speed, V. This V in glass will be different for water, different for air, and different for any other transparent material. This velocity in the glass. In glass is V. In other material, the value of the velocity in it will be different from that of the glass. So every material and the speed with which light travels through. Now, if we calculate the ratio of the speed of light in vacuum to the speed of light in a material V, the result is called the refractive index of the material here. So refractive index is the speed of light in vacuum divided by the speed of light in a material. So C over V. C for speed of light in vacuum, V for the speed of light in any other material we are interested in. The result is called the refractive index of that material. So when you do this for glass, for air, the refractive index for air is approximately 1. When you do the same ratio for water, the refractive index for water is 1.33. For glass, you divide the ratio speed of light in vacuum divided by speed of light in glass, your answer is 1.5. And every other material has got a unique a unique refractive index. That for air is approximately 1, that for water is 1.33, and that for glass is 1.5. For glass, 1.5 means you divide the speed of light in vacuum C by the speed of light in glass, and your answer is 1.5. The refractive index of water is 1.33. It means you divide the speed of light in vacuum by the speed of light in water, and your answer is 1.33. That is what it means. So refractive index is a property of all transparent medium, and it's simply the ratio of the speed of light in vacuum to the speed of light in that particular material. All right. So we can do a simple calculation. If you are told that the speed of light in vacuum, C, equals 3 times 10 to the power 8 meters per second. If the refractive index of water is 1.33, what is the speed of light in water? Then you can do the calculation and say that the refractive index of water is C over V. So you do the substitution. So here, V is going to be C over N, isn't it?
Yes, sir.
And so V is going to be C over N, and C is 3 times 10 to the power 8 divided by 1.33. And when you do this division, you know the velocity of light in water. If you want the velocity of light in glass, and you know that C for vacuum is 3, then you are going to say that for glass, velocity of light in glass is going to be the C over refractive index of glass. And that is going to be 3 times 10 to the power 8 over 1.5. And your result will give you the velocity of light in glass. So refractive index is a property of all material. Every material has a different refractive index. And because of that, we can calculate the speed of light in every material if we know the refractive index. I hope the point is made.
Yes, sir.
Okay, now I'm going to the laws of refraction. I've dealt with refractive index. It helps us to find the velocity of light in or any other transparent medium. But refractive index is a ratio of the speed of light. It's a ratio of speed of light in vacuum to ratio of speed of light in any other material. Is the refractive index of that material. Good. Now, laws of refraction. Come back to this diagram. The original diagram I drew. We have 2 laws of refraction, just as we have 2 for reflection. In the first law of refraction, look at this. We have 3 rays here. Incident ray, normal, and the refracted ray. And in my diagram, they are all lying on the surface of the sheet of paper. So the first law of refraction says that when refraction occurs, the incident ray, the normal, and the refracted ray at the point of incidence all lie in the same plane or lie in the same surface. This is called the first law of refraction. Take note of it. First law of refraction. The incident ray, the normal, and the refracted ray at the point of incidence, all of them lie in the same plane. You may be asked to state it, so take note. The second law of refraction is about the equation that connects the incident ray, the angle of incidence and the angle of refraction, an equation that connects the two. Remember, in reflection, the equation that connects the angle of incidence and reflection is that they are equal. I equals R. That is the equation that connects them. Question: what is the equation that connects the incident ray, the angle of incidence to the angle of refraction whenever refraction occurs? One man tried various methods and came up with an equation connecting I and R, angle of incidence and angle of refraction. His name is Snell. Snell. He was able to develop an equation that connects I, angle of incidence, and angle of refraction, R. His name is Snell. So the second law is named after him, called Snell's law. Now, Snell found out that when refraction occurs, he's trying to get an equation that connects I and R. Somebody's phone is making noise. Snell was able to develop an equation that connects the angle of incidence and the angle of refraction. And so the second law is named after him, Snell's law. What did Snell find out? Snell found out that when you take the angle of incidence, I, and you calculate the sine of I, sine is a trigonometric ratio. You calculate sine I, sine of the angle of incidence, and you take the angle of refraction, and you calculate the sine of the angle of refraction. You do these two calculations. You do sine I, and then you do sine R, and you divide sine I by sine R. The result you get is equal to the refractive index of the material in question. So if this is vacuum and this is glass, you calculate sine I, you divide by sine R, your result is the same as the refractive index of glass. If this material is water and you let light pass from vacuum into water, and you measure this angle I and you measure this R, and you calculate sine I and you calculate sine R, and you divide sine I by sine R, your answer is the same as the refractive index of water. So it means we have two ways of getting refractive index of a material. One is by dividing the velocity of light in vacuum by the velocity of light in the material. And Snell has also found out that you can get the same refractive index by calculating the ratios of the angles of the sine of the ratios of the sine of the angle of incidence and the sine of the angle of refraction. So Snell's law states that anytime refraction occurs, sine I, I'm writing it, sine I over sine R is a constant called the refractive index of the material in question. This is the second law. You can say it you can write it in mathematics like this, or you can say the whole thing in English. In English, you're going to say, something divided by something is a ratio. So Snell's law says that whenever refraction occurs, the ratio of the sine of angle of incidence to the sine of angle of refraction equals the refractive index of the material, or it's a constant. This is Snell's law. In mathematics, you can state it like this: sine I over sine R equals N, and say that I is the angle of incidence, R is the angle of refraction, N is the refractive index of the material in question. You are good to go. So refractive index can be calculated in two ways, either by comparing the velocities of light in vacuum to the velocity in the material, or measuring the angle of incidence, calculating the sine, measuring the angle of refraction, calculating the sine, and dividing, you get the refractive index. I hope the point is made.
Yes, sir.
Good. Now, that is Snell's law. But in doing calculation, we don't use the Snell's law as it is. No. There is another version of Snell's law which we use in practical calculations. If you're asked to state the law, state it. But when you have to do calculations involving refraction, there is a version of this law which we use. And I'm going to use the next 15 minutes to help you to know that version of Snell's law for calculation purposes. So take note. We are looking at the version of Snell's law that we'll be using in our calculations when it comes to refraction. Now, let's say we have a boundary here. This is a boundary. This is a boundary. Above the boundary is vacuum. And below the boundary, we have two different materials. So I'm using this to separate the two. We have two different materials, one here and one there. Here is a boundary between vacuum and two different materials. So I'll call the left here medium 1. And the right here, the right of this one here, below the boundary. This is the boundary, BB. Above the boundary is vacuum. And below it, there are two different materials. On the left is transparent medium 1. On the right is transparent medium 2. So here is medium 2. So above is vacuum. Below we have two different materials. On the left, below this boundary is medium 1. On the right, below the boundary is medium 2. I'm deriving the form of Snell's law for calculation. After I'm done, anytime you want to do calculations or refraction, you use what we are going to derive. Above is vacuum. Now, let the speed of light in vacuum be c, and the speed of light in medium 1 be v1. The speed of light in medium 2 be v2, and let the refractive index of medium 1 be n1, and the refractive index of medium 2 be n2. So I've stated the meanings of this. C is the speed of light in vacuum. Speed of light in medium 1 is v1. Refractive index of medium 1, that is when you compare the speed of the two speeds of light, this is your result n1. This is medium 2 on the right, be here. And the speed of light in medium 2, let it be v2, and the refractive index of medium 2 be n2. In other words, when you divide c by v2, you get n2. And here, when you divide c by v1, you get n1. Okay, assuming that light from vacuum enters the two media with the same angle of incidence. Parallel light from vacuum enter the two media like this. So in medium 2, it's going to undergo refraction. Medium 1 is going to undergo refraction.
Sadiq.
Is the teacher off now? Hey.
I think there's network problem. You experience network problem at his end.
You.
It's been almost time.
The first is This is chemistry.
7 more minutes to be 6. I think.
I
7. Yeah.
this is
7 minutes before.
baby. This is baby doing the other pan econo. Can I?
That's it. Never there.
They are doing better now. We know.
And say, oh no, I was not quite reading and say, understand now. No, here. I can kind of reading. Now, and you're a second, which I can answer.
That's it.
Oh, Charlie.
Yeah, Charlie. Enough for more.
My dad first house. My dad first house. My second house.
I think 6 minutes before time. 6.
Na first day, you can be busy out.
Charlie,
What's it?
This thing, it's noisy. It's noisy.
Charlie.
The lecture is back.
A family sukra.
Charlie, as much as
The man is
wow, yes, I call a if you are class out, I mean, James Nabu and what, and I miss as someone can mean Kumpu. Apart from Master, apart from infant, Menkabe, I met you.
And one way, Yankupo Bishra, what can you create by Yankupo Bishra?
Yeah,
I'll teach it again. That's just we be. But
Hello.
Yes.
This one they taught me in Form 1, there first one, year 2000. In science.
And you still remember, yeah.
In science.
Yeah.
Yeah,
I
still remember.
There's no concern.
In Form 1.
What's it?
That's the base.
Well, yes, a reflection and motion reflection the law of reflection.
Now, you're quite a business lady.
I'm here. So, I also concern. I
can't come motion. I know you. They are near basics.
This one, if you have
pure science. Very lucky.
I'm here.
I understand, sir. I understand, say be a basics, but sir, concave na concave na no drawing na.
Senior.
Hello.
What's a better experiment? First spoon fire experiment. Spoon.
Na drawing ke to win some kasa kasa. Yeah, so just see now they la na bia bebe chiri. Owi.
Ala just far to the wall. Masa. Maybe I'm
okay. Hello,
Sam.
Hello. I'm back. My phone went off. Okay, so I'm continuing from where I left off. I said I'm applying Snell's law to point P in between vacuum and medium 1. So sine theta here divided by sine theta 1 in the medium, because the refractive index of medium 1, and it's also equal to C over V1. I've written it here.
Okay.
Now let me go to medium 2. At the point Q, where refraction is occurring between vacuum and medium 2, Snell's law says that sine of the angle in vacuum divided by the angle in the medium, theta 2, that is sine theta in vacuum over sine theta 2 in medium 2, equals the refractive index of medium 2 is also equal to the speed of light in vacuum divided by the speed of light in medium 2. So we have two separate Snell's laws so this Snell's law for medium 1 and Snell's law for medium 2. I'm going to simplify them to produce only one equation that can be used to solve problems involving refraction. Now, look at how I'm going to do it. Let's take this. So, take medium 1. Sine theta here over sine theta 1 equals n1. So, I'm writing it sine theta over sine theta 1 equals n1. I'm only considering the left-hand side. This one, it means that when I take sine theta to this side, I move the sine theta to this side, I'm going to have sine theta in vacuum here equals n1 sine theta 1. When I do the same thing for medium 2, it's like this. Sine theta over sine theta 2 equals n2. When I move the sine theta here to this side, I'm going to have sine theta equals n2 sine theta 2. So on the left, I have sine theta equals n1 sine theta 1. On the right, I have sine theta equals n2 sine theta 2. So it means I can equate this, equate this and this. I can equate this one, sine theta equals n1 sine theta 2, 2 sine theta equals n2 sine theta, and write this n1 sine theta 1 equals n2 sine theta 2. This is the equation that is connecting the two. So anytime you are using the laws of refraction for calculation, this is the form of Snell's law you will state. N1 sine theta 1 equals N2 sine theta 2. N1 is the refractive index in the first medium. Theta 1 is the angle of incidence in the first medium. N2 is the refractive index of the second medium. Theta 2 is the angle of refraction in the second medium. This is the form of Snell's law. I'm writing it again. N1 sine theta 1 equals N2 sine theta 2. I'm mentioning the meaning of this formula. I'm saying that refraction has occurred between two different media. N1 is the refractive index of medium 1. Theta 1 is the angle of incidence in medium 1. N2 is the angle of incidence in medium 2. Theta 2 is the angle of refraction in medium 2. And this is the formula you are going to use. So if you are giving the value for N1 and the angle in medium 1, you are giving the value, the N2 in medium 2, and you have to calculate theta 2. You do it. If you are giving angle theta 2, you are giving N2 for the second medium. You are giving the angle in the first medium. Calculate the refractive index of the first medium, then you do it. So this is the practical form. The practical form of Snell's law. I hope it's clear.
Snell's formula. Okay.
So take note of this. N1
halfway.
Okay. So let me give you an example. All right. Let me give you an example.
Okay.
Let's say light moves from water into glass. All right. Light moves from water into glass. And light moves from water into glass. And you are told that the refractive index of water is 1.33. And the angle of incidence in the water, theta 1, equals, let's say, 20 degrees. Now, the refractive index of glass is 1.5. These are standard numbers. What is the angle in the glass? What will be the angle of refraction in the glass? Something like that. Above is water. Below is glass. This is the normal. Light moves from water and enters the glass. The angle of incidence here is 20 degrees. What would be the angle of refraction in the glass? You are told that the refractiveness of water is 1.33. The refractiveness of glass is 1.5. Calculate the angle in the glass. Then you are going to state that N1 sine theta 1 equals N2 sine theta 2. And then you do the substitution.
Yes.
N1 is about the water. N2 is about the second medium, right? So N1 for water is going to be 1.33. Sine of the angle in water is sine 20 degrees equals N for glass is 1.5, and then sine theta for the angle you are trying to calculate, sine theta in the glass. Then you simplify all of this on the left hand side and divide by 1.5, and you have 1.33 sine 20 over 1.5 equals sine theta in the glass. To do this, you have to do sine inverse. I hope you know how to do it.
Yes, sir.
So theta is going to be sine inverse of all that is in bracket 1.33.
That is 1.33 sine 20
over 1.5.
1.5.
Yes, and that will give you the angle in the glass. So the practical form of Snell's law for calculation is N1 sine theta 1 equals N2 sine theta 2, etc., etc. It's 6 o'clock. Let's end here.
All right, sir. Thank you, sir.
And then look through the questions and do some more calculations, right? Yeah.
Okay, sir.
Yes.
Okay, sir.
Okay. Yes, talk.
Let's say a question is given. Let's say a question is given like the one 1.33, and the angle for incidence is, let's say, 56. It's always possible. It's always possible for the angle of incidence should be greater than the angle of the refraction.
Yeah, it depends on which direction the light is going.
Okay.
It depends on which direction the light is going.
Okay.
So you always use the formula I've given you in the box. This formula is what you are going to use for your calculations as far as refraction is concerned. Okay.
So I hope Thursday you wish to meet him. Maybe same time.
Okay, so we can meet on Thursday, right?
Yes, sir.
Meet on Thursday, and then we can finish up with the refraction. And then the weekend we go to maybe wave
and we get our group
like that, right?
7 to 9 in the evening. That's
okay. All right. Have a good
in the evening.
Yeah.
Okay,
Thursday,
sir.
7 to 9.
7 to 9 in the evening.
All right. Thursday, 7 to 9 in the evening. Right.
Okay, sir. Thank you, sir. So you can leave us, sir. Hello.
Yeah, guys.
Hello. Hello, societal meeting. Namasa.
What's it?
Mr. Isaac.
Yes. Mr. Yes.
Ore pacho moi adumbidum na GHS munya science teachers na wacha mna moti asono ya pamuchopi yes schedule na mombo anya anta ko teacher no nso teacher no oti ase nti no ka hu say simple nti wo ka say go over again sir na spend time nti bia mo di sa diagram no draw na sa convention na focus na middle point na ade no
So what's just one you home?
Mame bro me kakra.
JHS na mkwano na different.
Me the mate me akire mu ye conductor and insulator unit 4 session 1 asa.
Yes.
I know there. You want to
Unit
hear?
4.
Yeah, can light once a reflection and reflect.
Yeah.
na there be say no say ka oka GHS na say GHS the na pure physics o no ya bibi ate say GHS nze no say kan to mo amoye science o SHS no mo na
Because
bet mo
Oh,
boy
well, yes, SHS.
who
So,
said?
who yeah, elective SHS scribing that integrated science. No, who now? I just said, oh yeah, science and kasa like elective
So
phases.
elective phases.
Ala. Madam Vic Wati. Nti wudi winning. One say yes chance no initial no or draw a DB nothing. On my 4 or say or come 4 pub. Oh, what's the 4 BB? What's the back way? That 4 reason on. For reason. How he got the 4 reason? Me can reflected ray and pay. No back who became count.
Reflected in
How
a
it came
character principal axis and the center
Center
reflected
of curvature. Yes, and then
oh
so that one, the way I OC emphasize also, it means that everything can happen. So on our bar, he always focus on the diagram aspect because he know what he's doing. Oba, he always
you
focus on the
see,
diagram
the
aspect.
thing is,
Obi knew.
like, yes, I didn't tell yes, and he said, theory aspect, no. They can draw the diagram for you. So is this focus anyway now will be determined, say, is it a concave or convex? Is it a way one? You can't solve it.
Madam Vic in patch, always how born no mammy na. What
me
the kakra na obeji ya yes classes.
Mr. ne number there ti so hu mi answer Mr.
Abua. No, they mean also why. Many.
me mau practical bio try na so what try ya one obeti na say fa spoon on baby edidi no na hwem bon say o make no be from be invert na fa na chi no na hwe bon so make be ye there's no invert he on the chi on na like exact so you saw no aka obeti as but you see different agency the same
With that concept, no.
Who say that
But
concept in the
look at,
so but who your calculation now?
but look
Because
at how
they can place the object
across it. Who say across it? Nah. As I cross it, I say a bit chimbe.
On say so first no baby did no I say you a holoform. What I say?
Maybe I can match as you, but they are making it. And then, see the what you be at work classes independent on Tiasia. Then I do like how I need feel. Once you don't try, they are meant to say, me who be a teacher or person. Today is my first time.
Mopa your center. Or a very good power on your science, your friend Presla. Mama Tia says, hey,
that is a
no man. Who did you? Kakakwana say you train a better as ya own. Maybe okay because masa
for YouTube na boshimwe. What I say?
The best thing is go to YouTube, okay? Just go to YouTube. YouTube now. I'm better. I'm church and the camera. It's me waiting to go show YouTube.
Into YouTube. So one you know SHS. I miss me you know SHS. Nti one you know SHS. Because of YouTube na koboshim.
It's not easy.
Where sure say YouTube one. Where sure say YouTube one can. Where sure say YouTube one can. I brought for our account. Won't be away now. What's this?
Dabi obey simple. Obey simple.
Oh yeah, lecture engineer then. Mami who you know what?
Like
but I've feel the pains today. So we try the pan and the pronoun.
Won't say they make a glass now or the chair no. Your officers like your one who physical. Into like it very but the better what I say. And then the lens na ding na obo mirror in light bulb light reaching na obo until obey that can but you say one message just the man just so cool YouTube na the make character time mission until you catch them so time mission YouTube.
Oh,
YouTube.
but your quiz nobody, anybody, a big deal. Quiz
Oh, they say.
Oh, quiz ni I be quiz no. Quiz an say be.
But for who say the main aspect we so na easy so.
I be who say baby I who fiba no. I be easy amount. Who say when he started the lights, that is the incidents we reflected ray, those kind of things. No. I got a science teacher in JHS. He took his time not cheating me. So that aspect, I really understand. The new training pono, I was like, I do want to be more. So all children when I'm then I got to know some and be more because this one to all children. The person understand it like to the grassroots. The Nipano, I don't know channel we can decide not to pay attention. What else? But as well, I begin to feel how painful it is, Charlie.
Feel kwa na last semester kwa na confuse pa na we say da na last semester na confuse pa a cha say no and what take care dia I want na confuse pa da we yes trick bi an shada nim sa
Tio. Physics, last semester. No? It was last semester. It was about thermometer and things, those kind of aspects. No? That one too. I was having fair idea about it. I was not able to go to face, but to me, yeah.
When practical no Dawson. So when you practical aspect never how practical no Dawson. I said when you do electricity from pool.